This video is going to explain a couple of aspects of rates of reaction that allow us to try to explain why rates will change and what those rates or changes are based on. And so one of these is this notion of collision theory. So again, rates are kind of hard to study because they're occurring on such a tiny scale in terms of what's actually happening. And so collision theory is one way they try to explain things. And then the other is the activation energy and how we can look at an activation energy in the context of reactants and products, and we do that with diagrams and those potential energy diagrams. So let's get going on this one. So collision theory, not surprisingly, states that a reaction can proceed only if reactants collide. Seems simple enough. Clearly there's not going to be any reaction if the particles do not interact with one another. So that makes a lot of sense, but it's not quite that simple. Reactions do need to collide with an orientation that is conducive to new bond formation. That is, the particles need to come into close proximity to one another where this new bond is going to get formed. If the orientation is not sufficient, the reaction may not proceed. And particles also need to collide with sufficient energy to allow for that bond breaking and new bond formation. And that should make a bit of sense to you, because if some energy wasn't applied to a system of reactants, if they just reacted spontaneously, well, that would probably be a problem, because there wouldn't be very much that it would ever be stable until everything was at the lowest sort of energy state. So let's look at a couple of these things first. So first of all, let's look at molecular orientation. That is how particles can orient with one another in order to generate a new product. So what we're going to try to show in this little demonstration is how molecular orientation plays a role in reaction rate, because it can actually determine whether a reaction proceeds or not. So what we're looking at here is a reaction between potassium, that's K, and iodomethane, CH3I. And so incorrect orientation first, and you can see we're going to form Ki. And so in order to form Ki, the potassium and the iodine need to be in some sort of close orientation when they approach one another, so that they can establish that strong intermolecular force, that bond. And so if they're not, in that case, potassium collided with the hydrogen atom of the iodomethane, the strong force of attraction with potassium iodine cannot be formed. It certainly isn't strong enough to overcome the already strong force between iodine and carbon. And so in that case, because orientation wasn't appropriate, the reaction didn't proceed. Well, if the orientation is correct, if we rearrange or change the orientation a little bit, we can see how it's going to proceed. So now these two atoms are in close proximity. The force of attraction that forms between them is sufficiently strong, stronger than the force of attraction carbon and iodine. And if that's the case, a potassium iodine bond forms, and you form potassium iodide. And the other product of this is a methane radical, CH3, with a lone electron, and that is how correct orientation will allow the reaction to proceed. Okay, so that seems simple enough. The orientation has to be conducive to the formation of these new electrostatic forces of attraction, these stronger electrostatic forces of attraction. You can have a collision at high energy without having a reaction, because the orientation is not allowing those new stronger forces of attraction to override the current, the bonding that is already in place. So that's molecular orientation. Seems pretty straightforward. Well, how about activation energy? Well, this is pretty straightforward as well. So let's see this. So here we have a potential energy diagram. So potential energy on the y-axis, reaction progress on the x-axis, and we're just going to go through this, and you'll see the different changes that we can indicate on a potential energy diagram for this typical reaction, nitrogen dioxide plus carbon monoxide. So let's have a look at see how things proceed. So what we have here initially is the process of bond forming between, as you see, an oxygen of the nitrogen dioxide and the carbon of carbon monoxide. So the bond begins to form, and that's why it's sort of a squiggly or dashed line. It's not a true chemical bond yet, but it's in the process of forming. And this happens because the two molecules are coming to close proximity to one another, and electrostatic forces are starting to shift. An electrostatic force of attraction between the carbon of carbon monoxide is starting to attract the electrons of the oxygen of nitrogen dioxide. That said, that bond between nitrogen and oxygen is starting to weaken, and so the bond length actually increases as the oxygen atom is being pulled away by the carbon. Next, what we have is what's known as an activated complex, and this is again a short-lived species, and it's basically has two bonds, one being broken, one being formed, so they shouldn't be solid. The other thing indicated is the amount of energy required for this complex essentially to be formed. That's the activation energy, EA. So 132 kilojoules per mole. That's positive. Activation energies are always positive. You have to apply some energy to generate this activated complex. And so it's not really a molecule, because those bonds, you have one bond in the process of being broken, you have another bond in the process of being formed. So it's not really truly molecular, very short-lived, very reactive, and it's going to go one way or the other basically. And if it goes the way we'd hope, that is if a reaction proceeds, this is what's going to happen. So once again, what it's trying to show here is that now that bond between the carbon and the oxygen is stronger. That electrostatic force of attraction essentially has overridden the electrostatic force of attraction that was a bond between the nitrogen and the oxygen. And so we're in the process of forming CO2. The bond length is still a little longer because there's still some force of attraction from the nitrogen atom, but that bond, now you can see the dashed line, is in the process of breaking, so electrostatic force of attraction is weaker from the nitrogen to the oxygen. And then the reaction would go to completion, and we generate two new molecules, so nitrogen monoxide and carbon dioxide. And as it shows here, because the products are energetically more stable than the reactants, we have a negative delta H sign, and that means this is an exothermic reaction. And so 226 kilojoules of heat would be released into the surroundings in this reaction. Here we have an endothermic reaction. As you can see, the energy of the reactants is energetically lower than the energy of the products, indicative of an endothermic process. And so here in the first phase, we are starting to establish a bond between one of the chlorines of chlorine gas and the nitrogen of nitrogen monoxide. So there's that sort of pseudo bond forming, the dashed line, and at the same time that chlorine-chlorine bond is going to start lengthening as the electrostatic forces of attraction of the nitrogen start pulling one of those chlorine atoms away. As enough energy is added, there's sufficient energy available, the activated complex is formed, and so now you essentially have those sort of two bonds between the two reactants, so that chlorine-chlorine bond again lengthening in the process of being broken, and that nitrogen-chlorine bond in the process of being formed. And so 85 kilojoules per mole of activation energy would allow for the formation of the activated complex. Reaction proceeds, and again that chlorine-chlorine bond is now in the process of breaking. Electrostatic forces would be quite weakened, and that nitrogen-chlorine bond is quite strong. And finally, you get your product nitrosyl chloride, NOCl, and you would get a chlorine radical, Cl, and it would have a lone electron. Pretty reactive species. But the overall process, 83 kilojoules of energy, and that's positive, required to convert nitrogen monoxide and chlorine gas to nitrosyl chloride and chlorine. So endothermic process, 83 kilojoules of energy was added. So again, there we go. Makes a bit of sense. Any chemicals are stable. That's why they formed. That's where they're in their orientations that they are. And so the application of some energy destabilizes any given reactants. And if a sufficient energy is applied, those reactants will be able to interact with each other and form new bonds, form new chemical compounds. That is the nature of a reaction. So this can either be endothermic or exothermic. Just because you get an endothermic reaction doesn't mean you don't have to have some sort of activation energy. There's always some energy applied for a reaction to proceed. And so that concludes this video.